Hello and welcome to the last Basecamp talk of the summer semester 2020 that we are hosting together with BSI. Today's topic is practical deep learning. And first I will give you an introduction on the theoretical part, and then Benjamin from BSI will host a hands-on session where you can try out the things that you've seen in my presentation on real data. So let's get started. So what we do today is practical machine learning. And how to tackle this problem, there are these 5 core steps that you can follow to get your applied machine learning project running. So the first step is the exploratory analysis, where you look at the data and see whether it is possible at all to learn something from the data. Then the second step would be the data cleaning, where you have a look at the data to see whether this is all usable, whether there are some problems with it. Then you do some feature engineering to combine some features, maybe bring some additional features from outside. Once this is done, you can see the data you have and perform an algorithm selection. And afterwards, you train the actual model and evaluate this. So we can quickly go over each steps in more detail. So for the exploratory analysis, you would just start with a simple algorithm that you just apply on the data that you have. So, I mean, what is nice there is that there are decision trees, because you can also look up how they actually work, where they make these decisions. But if you want to go a little bit more advanced, you can use a random forest, because this classifier can capture non-linearity. And how this works, I'll show you a little bit later, but this is a very important feature of a classifier. And the main question that we want to tackle with this analysis is, how can we get, or can we get at all any meaningful classification from the data that we have? So once this is established, once we get some score that is good or is not good, we can step to the next step. This would be the data cleaning. And in this step, you check the data for errors. For example, maybe in your data set, you have some missing values. And to know exactly how to deal with those, you would actually need some knowledge from a domain expert with whom you work on this. So, for example, is there a default value that we provide when there is no none value given? This can be a 0 or maybe a 1, but it really depends on the context and the data that you have. And another thing you can do there is to detect outliers or wrong data. For example, if you have a data set on house prices and you have a price for a house there for 1,000 euros, this is probably not quite correct. Maybe it should have been 1 million euros. So this is something that you need to have a look at. And then after this is done, then you do your feature engineering. And you're checking your data, and you check how can you scale or normalize the data meaningfully. So for example, some data can have an exponential or logarithmic growth, so you need to scale it appropriately. And this feature scaling is important for training. So ideally, especially with neural networks, you would fit all of your data into the scale of between 0 and 1. So then every feature can be treated equally. And this does improve the performance. Yes, you can also think of whether you can use some data from before. If you have some, some time series, maybe you can also use some data points from maybe 5 steps before. Maybe they give you some interesting signal for your classifier. Or you can also combine several features to create new features that are maybe more meaningful than one feature in isolation. Another thing you can do there is to bring additional data sources for better classification. So, for example, if you're dealing with some sales from several days, then you can also maybe bring in the weather information from this day. Maybe you don't have it recorded, but maybe you can query your local weather provider to give you this data as well. And after you've done this, you can do a quick sanity check. So if you have now better data, so the data is cleaned and nicer, and you have better features, then they should, the performance of your basic algorithm should also increase. And if this is true, then we can select an algorithm. And this is based on several factors that are maybe related to the performance that you want to achieve, or maybe also to the practical constraints that you have. So, so if you have not a lot of data, then training, deep neural networks is going to be tough, because they do require a lot of training data. So maybe there, taking a simpler algorithm would be better. And you can also be limited by the training resources. For example, even if you have a lot of data, but you just have one old laptop, the training time is just going to be too much, and maybe it's not computable at all on this machine. Another thing is the classification time. So the training time is what we discussed before, but now it's about the classification time. For example, with modern transformer models for natural language processing, to classify a text there, it takes maybe 10 seconds. And this can be acceptable in a scientific case, definitely, but if you want to have a real-time application, maybe this 10 seconds are a little bit too large. So maybe then you need to skip or switch to another algorithm. And also whether you need to do online learning or not. So for example, the spam classifier in your email client, it does spam classification, and you can just provide the new training examples by labeling an email as spam. And then you expect the model to be instantly updated and not wait for maybe a month and be updated later on. So this is a capability that also not every classifier provides. After you've done this, you can switch to the actual model training. And before you start this one, you split your data into a training and a test split. So usually you would have something like 80% for training and 20% for testing. If you have a lot of hyperparameters to tune, it might make sense to also introduce a development set just for tuning of those parameters. So maybe you have like 70% training, 10% dev set, and 20% testing, something like this. After you've done this, you're training the actual model on the training data. This gives you this model parameters. And in the process, you also update and adjust your hyperparameters. And while doing all of this, you need to monitor your model for overfitting. Overfitting is where the model just performs very good on the training data, but cannot generalize to give you a good performance on the test data. Okay, so this would be the general approach for practical machine learning. Now we are going to talk about the training. So for machine learning, you usually have the objective of finding patterns in the training data. And the pattern would be any kind of correspondence between your input, which are your features, and your output, which is the classification label that you want to achieve. While doing this, you're trying to minimize the loss on the training data, and you're doing all of this under the assumption that the training data that you have is drawn from the same distribution as the test data. So let's say you're training for climate, and you're using testing data, training data from the 1960s, and you're applying this to the current year, then maybe this will not really work. So there you need much similar training data as the test data. And the loss or the cost function is a function that you do during training. So all of the misclassifications that you have, you are accumulating them into one loss, and this loss is what you then later try to minimize. The ideal loss function scales with the magnitude of error, so which means that the higher your error, the further you are away from the correct value, the higher the loss should be. And to minimize the loss, you compute the gradient of the error and use an algorithm like gradient descent to minimize this loss. And get a better classification performance. So how does this work in general? So you start in your learning process, and this is the loss landscape that you have. So you have feature 1 and feature 2 along those lines, and this elevation would be the loss that you have. So you would maybe start at this position, and then you would like to get somewhere where you have a very low loss. So this would be this area. So you start like this on this mountain hill, and then you see, check the direction of the ascent. So this would be into this direction. So you would just go into the opposite direction to reduce the loss. And once you're here, then you can also check again where is the gradient is the highest. So this would give you this direction, and you go step by step until you arrive at some minimum, or until you're done with your training. Yes, we have done this in the school, of course, for functions that are linear. So as you would see, I mean, here we have something like quadratic function, and if you are around here, then you know, okay, that you would need to go into this direction to get to the minimum. Yes, but what do we do when you have a multi-dimensional landscape? So you have a lot of features. There you actually use partial derivatives. And partial derivatives means that you just freeze all of the parameters but one, which would be in this case. So here we also have two parameters, like maybe this, and this would be the loss. So you freeze this parameter to one value, and then have a look at your loss landscape. And this is once again a linear function. So you can do the derivation into this direction, and afterwards you would freeze this dimension. No, you would freeze this dimension, so that it would give you the direction of this one, and you combine them, and this would be the direction that you need to take. There is this nice video that you can have a look at, so please do. It's explaining this really nicely. And I've also explained some of those things in more detail in this talk on machine learning, so or deep learning. So I can paste it into the chat. I hope I can do this. So it also has a recording there. I'm getting a little bit more into detail about these things, but now it's just so that you get the general idea how this works. Okay, during training, you can set several things. You can set the optimizer and your learning rate. For an optimizer, what you have seen now is this stochastic gradient descent. So you calculate the gradient and just go down your gradient to arrive at the minimum. And so this stochastic gradient descent is a nice and robust algorithm. But there are also some more modern ones. And for example, this ADAM algorithm is usually faster and also does perform very well. Still, there are hyperparameters that you need to set for both of them for the optimal performance, but usually the defaults also work quite nicely. Another hyperparameter that you need to set is the learning rate. And yeah, and there you kind of have a trade-off to do with. If you have a high learning rate, then you are potentially converging faster, but it can happen that you skip over optimal solutions. So since I cannot draw here, let's go back. So let's say you're now at this red point, and you would like to go maybe until this lowest point. But if your learning rate is too large, then what's happening is you are just jumping to the other side of this valley, and then you're checking your gradient. Okay, now you need to go into the other direction, and then you switch again. So this might mean that it can happen that you do not reach the minimum. With low learning rates, you can get more accurate minima, but the one potential problem is that you can remain in a local minimum. So sometimes you need to skip some of the local minima so that you can get to a maybe global minimum, or at least a very good local minimum. So far we've also talked about overfitting, and this is one example from Wikipedia on this page on this topic. So here you see two functions, a blue one and a red one, and they both are completely different except for a few points. And it seems like the blue one is a lot more sophisticated. So it has, yeah, it's twisting and turning much more than the green one, which is very calm and slow. And this, it might be that the blue one is actually does overfitting, so that it's really tightly handles all of the training examples, but maybe that's not generalized too well. So probably the green one can do performs worse on the training set, but because it's it does not have too many parameters, so it's not as funky as the other one. You can get better classification performance on unseen data. So to prevent this, we use regularization. So what we do is we are just adding another component to your loss function. So this would be your loss function. So you're applying your function to your input, getting an output, and then calculating some kind of loss and accumulating it over all of your training instances. With regularization, you also add this regularization term for your function. And this lambda is the trade-off. So it's a factor to scale the regularization. How much do you want your model to perform good on the training data, or how simple or more general should your model be? For regularization, there are like this would be the most common regularization options that you have, L1 or L2 regularization. So for L1, you are just summing up the absolute values of your feature weights in your function, and for L2 you sum up the squares of your feature weights. So they are both working on minimizing the model complexity, but with L1 many values can become 0, so that there is maybe just a few ones, the most important ones, that have a higher value. And the L2 regularization, it penalizes higher values much more, because it's a quadratic growth here. So that's why it reduces the number of high values, and you have a lot of values that are close to 0, because this is where the regularization is the lowest. For deep learning, especially, there is also another kind of regularization that you can use, and this would be dropout. So what do you do with dropout? You are just deactivating some layers in some nodes in your layers. So maybe you are keeping 50% of the nodes, and the rest are just deactivated during training. And that way, if there is some nodes that give you a high input, in 50% of the times it will be deactivated, so that the network should not just rely on those highly significant values, but can also utilize information from the non-deactivated ones. Yes, so this makes the network more robust to some input problems, and also reduces overfitting. However, since you are removing half of the nodes, this would mean that you would need to train it for maybe twice the amount of epochs to get to the same performance. Okay, and now a quick overview of deep learning. So as said before, I've dealt with this more extensively in this talk. So this is very rough and quick walkthrough of this. So in deep learning, we are doing machine learning with deep neural networks. So these neural networks are called like this because they're kind of inspired by the neurons in the brain. So you also have these neurons in your brain, and then they get some activations, and then they fire, and this is how you think. But the nice things about this is that neural networks perform some automatic feature extraction and combination. So actually, you don't have to spend that much amount on this third step that we've talked to before. And it also has this layers of processing. So for example, in image recognition, you would start with identifying lines and then combining those lines to identify such shapes. And then maybe some shapes can be identified as an eye, and something that has eyes on it is then a face, and some object with a face is maybe a person. So it gives you this this nice learning of all of these features and automatically. So this is very nice. And they, since they're computationally very expensive, they benefit greatly if you have GPUs in your system, which for this BSI Brains that we are going to work with today, we definitely have. So that's good to hear. In general, this is how your neural network looks like. You have an input layer, which are the features that you can get from your data. Then you have one or usually several layers, hidden layers, and they produce some output. So here we would have 2 output neurons, and this could be your different labels. If we're doing sentiment analysis, this could be the positive class, and this lower one is the negative class. And at the end, we are checking which one has the highest activation. So let's say this is the upper one, and then we say, okay, this example has been a positive one. Yes, one neuron looks like this. So it has several weights. And it has one weight for each of the inputs that it gets from the layer before. And what you do then is you multiply the weights with your input and sum them all up together. You also have this bias weight here. So like an initial activation that's always there. And after you've summed up all of them, you put this result into the activation function, and this would be the activation of your neuron. The learning in the neural network happens like this: that you feed your inputs through the network, through all of the hidden layers to arrive at the output. Then you check whether here the positive class is actually the one that we wanted. If it's not, we wanted to have the negative class. Then in each of those neurons, you can check where the error is coming from. So if they did misclassification, then you can check where it was the highest. And and there you are also building your gradient and update the weight so that it works better next time. This will be roughly it. And usually what you do is you're compiling the loss on the output layers, not from one example, but you are taking mini batches, is how they are called in deep learning. So maybe you're taking 20 examples or maybe 100 examples to get a more accurate estimation what your actual gradients should be like, because one example is not that meaningful if you have a very large network. And you're doing your training for several epochs. So one epoch is when all of the input examples from the training data have been processed and their weights have been updated. This can also take a lot of time to train it, maybe through hundreds epochs, depending on the complexity of your problem and the layout of your network. Okay, since this is also a practical talk, maybe you want to see how you should design your network. So, and the structure that it should have, it's something like a funnel. So you're starting with maybe a lot of input features, and then you are reducing them subsequently more and more. So that at some point you arrive at your classification. So this would be a number classification, which starts as a pixel data, and then you're combining them all together to arrive at your 10 output values for the numbers 0 to 9. If you're having this funneling structure, then you're forcing the network to recombine features and find some meaningful correlations between them. Usually it's nice to have many layers because they allow you to do a lot of combinations of the features, but you should also be aware that you can also treat a neural network as a kind of as a memory. So if the network is very large, but your training data is not extremely huge, then what can happen is that the network actually learns all of the training examples. It achieves a perfect performance on the training data, but then it's catastrophically bad on the test data. So it's best to start with a smaller network and then maybe see whether additional layers increase the performance or not. Okay, so as I talked before, the neurons have some activation functions that are being processed. And so if you don't use any activation function, then you basically have this linear or identity activation. And what you see here, I can maybe quickly explain. So on the right side here in this positive value, these are the space of where we are making an error on this neuron. And this would be here on this negative side, this would be the ones where we are achieving the correct classification. So, this means that if we are here, then maybe we know that here the derivation is 1. So then we need to go into this -1 direction. So we are going into this direction until at some point we are past this point, and then we are classifying correctly. Yes, however, since we also get the same derivation on the correctly classified ones, we are actually pushing the border a little bit too much. So this can lead to overfitting because we are still continuing to push the weights into the direction where we are actually already getting a good performance. So this is maybe something that is not that good for networks. I mean, what you can think of is that you're doing this step activation. So you have this error class. When you're making an error and otherwise it's just 0. This could work, but actually it does not. So you cannot do a derivation on this one. So if you're here, you do a derivation, this is 0. So you do not know whether you need to push it into this direction or this one. So this is not good. What is good is something like a smooth step function. For example, the sigmoid function. It's especially good to differentiate between two classes because it has here around 0, it has the highest inclination. So it really spreads those examples apart. And here some learning is happening. Here, the nice thing is that if it's very low, then almost no training is happening here. So the correctly classified ones with some distance, they're good. But this also affects those examples here. So if something is here, it's misclassified, but it will still take a long time until it gets here to get to the right side of this equation. That's why we have this ReLU function, which is one of the most famous one or most commonly used one. What it does, there is this good linear function in the error class, and then just nothing on the correctly classified one. So we are not learning from positive examples, but pushing the negative ones linearly into this direction. So this is good, but it also cannot learn from already good, well-classified examples. And to handle this one, we can introduce this leaky ReLU function, which also can learn from the correct examples, but at a much lower rate. So you see that the inclination here is much lower than here. So it does still learn, but at a lower rate, and this is good. I also talked a little bit about universality and nonlinearity, and to experiment with this and with a lot of the other settings, there is this TensorFlow playground that I can show you here. So let's just say, okay, we have this problem. We have two classes, and we want to differentiate between those two. So we are having, like two features, so the x1 and x2, and we're feeding them through a network. So let's just do this, and you see that, I mean, it's just classified correctly straight away. So this is nice, but of course there are also these cases where it's not linearly separable in this case. And here, if we are using a linear activation, we are getting frame loss of about 50% and test loss also about 50%. So how can we counter this? We can either use nonlinear input features. So this would be x1 squared and x2 squared. If we use those, then once again, we get a very good separation in a very short amount of time. Or we cannot use this one, but use a nonlinear function, which are all of the above. So let's use ReLU, as said before. And this is always randomly initiated. So maybe for you, it's very fast, the conversion. Sometimes it's very slow. I'm not sure whether I will getting it here. So maybe I can just, okay, see, now it's very fast, and we have this, this good classification. So what you can also play around with is learning rate. So if we set it to extremely high, 10, then you see that it cannot learn. So sometimes it switches from one class to the other, but really it cannot learn so much. And with a very low learning rate, this whole process can take quite a while. And for some data sets like these ones, maybe it can also have troubles with conversion. Yes. So this tool actually does look similar as the one tool that we are going to use today. And this would be also the last part of my presentation. So the conclusion. So I've showed you today how to do a practical machine learning task. So if you're following these 5 steps, you should be good to go. And I also hope that you have some understanding about network engineering and what these hyperparameters mean. And also that you now know what overfitting is and how what some terms mean like ReLU or ADAM, so that this will help you in understanding papers and some lectures. And maybe you are now motivated to try out some neural networks, which we will get to now. So we are going to do this with this online tool provided by BSI, BSI Brains. There you see it's quite easy to use. So everything is drag and drop. So you're just getting your input features, then connecting them to your classifier. This is a neural classifier with these 8 features that we have here. And Exactly, and the backend is based on deep learning for J. So it's a Java framework for deep learning. The performance of deep learning for J is classification performance is yeah, basically the same as TensorFlow and Keras and all these Python frameworks. However, training and testing do have some additional load because it's this object-oriented Java setting. So the training times can be a little bit slower than if you're just using pure TensorFlow on your GPU. But still, it's for practice. This should not affect us too much. You can configure your network structures basically the same way as in this TensorFlow playground, and you can always check and tune your hyperparameter settings. So this would be the network setup. So you can just introduce some additional layers, and you can check here how many elements, how many neurons each layer should have. You can have a regularization even for each individual layer. You can set an activation function. Here it would be relo, and you can initialize those, for example, zeros, ones, or some random distribution. What else? Yes, you can also set training parameters. For example, how many epochs do you want to train the model on, and what would be the batch size? And yes, and here this updater is the optimize that we talked before. So this would be this ADAM, which called adaptive movement estimation. So it's a very good and optimizer. So because it has an adaptive learning rate for each individual training parameter, training feature. This makes it very good. So it's very fast and converges nicely. And these beta hyperparameters, these are the default values, and they work quite well in practice. So there are some resources also. If you're interested in neural networks, then there is this free book that you can read online. It's very nice. You can find it in the slides, and the slides are also available online. So I can maybe also post them in the chat so that you get access to them. Yes, so this would be from my side. Maybe we can do a short round of questions if there are any. And then we are getting to the practice, to the actual hands-on session.
Hello, everyone from my side as well. You have been introduced to quite a few bits and pieces already. So I'm going to do my best job at keeping this brief. I'm Benjamin. I work for BSI, which stands for Business System Integrations. We are a company that does a lot of software stuff, and this is our newest project or product, BSI Brains. Why is it called Brains? I'll come to that. To the structure of this part, we'll do 3 sections. The first section is like a little introductory section where we are going to, or I'm going to explain certain stuff to you and going through one exercise with you. The second part is we are going into split into rooms where you can then say whether you'd like to have an English session or a German session. We can provide both, and where you will do one of the exercises with, well, or alongside of a person of BSI. We have these like bracket BSI people here around. Thank you very much. And for the third part, you will be on your own. You will try to make a model as best as you can with the given data. And there is prizes to win, which I will come to later. So first on, can you see my my screen? Everything is right? Good, I see him nodding. So keeping this brief. This is the user interface of BSI Brains. So we have this part here, which we call a brain. And on the right side, there's the thing we call a mindset. What are these two? How do they play together? So the brain is basically the place where your inputs and input, output, and calculations happen, and the mindset is like the control center of what is happening to this data. Here in this part, for instance, we can have one brain training with multiple mindsets. So we have like a data set to that. So like data we've read into it, like from 2 different places. This is a weather forecast. So you have like one from Zurich and one from a nearby mountain, or like Hamburg and Hannover would be valid as well. The mindset control shows you at what stage is the brain, like is it untrained? Are you loading it onto the engine? Is it actually actively training, or can it be executed? In the lower part, you see the statistics. So this is actually, well, put together from a cortex that is running. We will get to that later. But there you can get a quick overview of how your network is performing. So we have different parts, like different elements in our brains. We have the inputs. Well, you saw the neurons, they're blue. We have the outputs, which are brown in our case. We have all learning steps, which here's a neural network in orange. All the static conversion, so it's like a function basically put into a UI step. They just do static conversion, like from string to integer or whatever it takes, or like split up your date into 3 dates, as you can see here. And then we have like analysis cortexes, so they do not learn, but they after it has learned, it applies certain like functions or plots to your data, so you have it more visual. To the cortex, which is the orange part, you see there's like this common part and the cortex specific part. Common is always inputs and outputs, because you need to drag and drop stuff into it. And there is the middle part, where in this case you can actually say how many layers and what kind of layers it's going to happen. So, but this is always the structure of the program and how it's going to work. For cortexes, you always have statistics, which you can look at and see and use as visualization for mindset, as you can see here. As well, you have logs. So if anything ever happens wrong, or just sometimes stuff happens, so it tells you something and what has gone wrong. We will be there to assist you. So to go over this quick, with the orange parts are usually supervised learning, and the green, well, the graph cortexes are unsupervised parts. Like in one forward propagation, inputs go into the training, into the neural cortex. Data comes from the outputs and goes back propagated through the graph cortexes into the training. So if you wonder why you always drag from left to right and the data flows from right to left, don't worry, we'll handle it. To go a bit deeper into what kind of data can you process, there is here a little marker to say what kind of data is it. Is it a scalar, vector, a matrix, or a tensor? We call it that. It's not like industry agreed upon, but in general, if it's like one value, we call it a scalar. One many, one row, it's vector, and so forth. So you can configure that and also pass this into a network with us. For today's session, we'll probably only need scalars, but we'll see. So there's vector stacking. You can say you want one, like you want to have an to calculate upon a vector. So, but you have 5 different scalars, so you can just stack them up on each other, like you see here. If you need it, we can come to it back later. I'm just rushing through. If it's like too fast, please say so. But otherwise, I'm going through this at the pace. So if I see nodding, it's like too fast, okay? Good. these are the supported types. So we have all real numbers, booleans, dates, binary resources, text, and input. Today we'll mostly focus on real numbers because those are the data types that we have today. But of course, we can also do like image recognition, so images and binary resources are important. This is the main UI. Here you see like how we've imported data. We've encapsulated them into data sets. And there's always we've talked about data splitting, so you can manage data splits. You can have one data set and multiple splits on that data set. So here we have a classical train test split, which if you can see it in subsets, but like to visualize this a bit better for you, like this would be all the orange ones are training rows and all the blue ones are testing rows. So you can do this automatically. You don't have to do any of this by hand. So as you can see, all the inputs have like input names are very much strongly correlated to the data column names. So our software does the stitching for you. You don't really need to handle all that. If you have ever done machine learning in other frameworks, it's a bit harder. Our mindset, once you come to it, you give it a name, you choose a data set. If the inputs and outputs are not yet allocated, and we'll see that soon, we can generate them so we don't have to do much work. And then we can select the test and train split to actually operate on this data. We'll soon be done and get to actual software, I promise. Here, if we ever get to import data, of course, it's also possible. If we have a data set, we can already map certain columns to data in our data set or data in our brains. And if the encoding is wrong, you can always set certain encodings to better match your data set that you have. Now we finally arrived at this. What are Glasse? BSI is a partially Swiss company, or mother company is Swiss, so Glasse are ice cream. And we're going to predict ice cream sellers today in all three of the stages, actually. But in the first one, we are going to have a rather small data set, and we'll have 20 years of daily values with our date, which is not important to training, but we can use it to visualize the duration of sunshine at that day and the number of ice cream sellers that were around. So we are going to create a brain which predicts how many ice cream sellers are present. And we're going to do that live, I guess. So let me get my browser up. Can you see my browser? Good, I see nodding. Here we have a bit of a bigger one that I've just opened, but let's create a new one just so we see the process of it. The accounts that you will get in your small groups, when you go later into the smaller groups, the BSI people will assign you an account and send the login data to you. You will not see so many things. You will just see what you need. But if I go to datasets and search for Glasse, for instance, I see that I have a dataset here which has 7,412 samples, which is exactly what we're going to work. So we're creating a new brain, I guess. New brain, there we go. We'll call this Basecamp brain. Going to step and just call this quickly. And now we can select the data set Here you will also only see one, so you will be fine. As you can see, we have no brain inputs and outputs in our newly created brain, but we can press down here, brain inputs, let it generate for you. Oh, maybe it's the wrong data set. Let's take the other one. Yeah, better. Okay. So as you can see, it tried to match what you probably want, like there's sun and glasses and the date, and it says, okay, let's create like inputs for all those three. But what we want is we want to predict this. We want to predict how many glasses are sold. So we probably want to create brain outputs. So as you can see, color changes to brown. It's going to be fine. Let's click OK. It also magically does that for you. We can select a data split, and train test has already been adjusted fine for us. So there's a lot of magic happening trying to figure out which ones you probably want. As a train set, we want training, and as a test set, we want testing. So that's going to be fine. Now we can just save it and be right in there. So it is already assigned two inputs for us, like a sun input and a date input. What we can see from the data set, this has already been set to a data type of type date. We are not going to use that one right now. So here on the right side, we have the archive of all the different steps that you can have. So there's all different machine learning algorithms. There's genetic programming, there's Gaussian process regression, and all that jazz. We are going to focus on a neural regression. Before we've talked about classification, like different numbers, but what we want to do is we want to have a regression. We want to figure out a specific value. So we're going to take a neural regression. By the way, if you're lazy to scrolling, you can just like type regression, then you will also find it. So here in our neural regression, we can open this and we have a rather blank slate. So we want the input type not to be decimal any, but decimal, and the output is a decimal vector. That's fine. So we can take this here, connect it up, take this here, connect it up. And now we're basically set for the beginning, but as you can see, there's a blank slate. We could either go in there and create, well, layers by hand, but I'm not going to do that. I'm going to let the software take stuff out for me. This was a little click on this brain symbol. And what it does, it takes in the input data that you have and figures out, well, on these inputs, what do I know from machine learning to actually generate you a network that works for this kind of problem that you have? So if you have inputs like pictures, it will probably generate you a convolutional neural network instead of this. We will see the funnel shape that we've talked about. Here it's number of inputs is 512, which is probably way too much. So we're going down to 32, and here funnel shape down, so 16, and then number of outputs, let's go to 8. That should work fine. Here you see we have blue ones, which are input types. We have brown nodes, which are output types. And on all these types, we can set the initialization, we can set the activation function. So let's go in there. This is a dense layer, as you can see. We have input, dense, convolution, sort of, but we're going to focus on like input, output, and dense ones for the moment. So the tool tries to approximate what you probably want to do. But here we have initializations, different ones. We have Xavier initializations, identity ones. If in doubt, just use what the tool gives you. It's what I do all the time. And we've talked about activation function, which is here ReLU is pre-selected because it's pretty good in most cases, but you can have like sigmoid, as we talked about, or 10H or whatever you want. What is important is that here you can mess around with those, but in the output layer, for regression at least, you should always go for activation identity. If you let the brain automatically set up, it does this for you, but if you don't, just keep that in mind. So here in train parameters, as you've seen, we can set the number of epochs. Let's just go down a bit to 20 because I don't want to bore you. And let's go up in the batch size to like 16. That should be fine. Here we can configure the updater. Let's just keep natom. It's going to be fine, I guess. And the regularization, we have these L1 and L2. And here we have the dropout regularization that we've talked about. 0.5 is probably going to be fine. Metrics. This is what's going to be shown later in statistics. And we're going to use the mean and the RMSE. So good. Okay. And basically, we have set this now up. We have our inputs. We have our neural regression all set up. We can give this a name. Who knows? And we have our output. So data is all linked up. This doesn't need to go anywhere. And now we can basically hit this big train button. It will now compile basically the brain that you've made, all the layers, into a machine trainable object, and then send this up to the ML engine, which happens in this step, by the way. So there's the UI and an engine in the back. So this tightly packed machine understandable model then gets trained. All the feedback that we get is displayed whenever we get some, and then we have this visualization here. So for instance, we've just trained it all. Our log says, well, it's done. It was done in 22 seconds, so quite fast, but it's a very small and a very it's a very small network in general, and with few epochs. So if you go in here, we can see the statistics a bit better and be like, okay, it's going down. I guess that's good. Let's give ourselves some more visualization power. And here we can, boop, where is it? Sometimes I don't find stuff and then I'll just type it out. Graph. I want a graph. What do I want to graph out? Well, I need one for my glacé and one for the date, I guess. And here I have my x-axis is probably logarithmic scale. I'm going to use the date input and format it as date time. All our inputs and here for graphs are ints, or just like regular numbers. So we can tell it to format it like a date time. And we will probably want our first series to be the input. So what is actually happening? Test, no transformation. Here we can choose like colors and all that jazz, but we're not going to. We're just going to say it's going to have straight connections. It's going to be fine. So we have inputs, and we're going to add another visualization output. Here we're going to select the glasses series output. So put it back to dataset type. You can either specify whether you want to display like training behavior or test behavior. So we're going to select test behavior here, which is important. Transformations we don't need, but you can toy around with all of these things later on. And we're also going for straight connections. So maybe input and output aren't the best names because, well, we have this here, this is the input and this is the output. I guess we can do better. So let's edit this because this is our prediction. On this side, we're going to take in what the brain tells us, and on this side, we're going to have the truth to that, or actual value, or whatever you want. Important is that here we have now two inputs and two outputs. So our date object, as you've heard before, is we will need to transform this into some kind of integer or long kind of type number. For that, we use time span, and you can connect this here. This is the time span step is configured in a way that it calculates the time span between the feature and some reference date. And if you've done some programming, this date will, you will know it. It's just the standard reference date, so we'll use it here as well, and that's what the standard is, and we don't need to configure it further. So in goes a date, an actual date object, out goes a number. And let's take our prediction from, yeah, that's going to be fine. Take a prediction from the neural regression network, and on the other side, we're going to connect the glassy. We're going to have a problem here because we don't have an output that matches this, but we don't need to because the date is only the x-axis. It doesn't change. There's no two types, but then we need to go here to this little like configure button and select the following. When data is missing, replace it with a default value. That's what we remember when data is missing, that we might want to either throw this data out or replace it with some default value. That's how we do it here. And press OK, it's going to be fine. I've done this only once today. So now with all set up, we can hit learn again. And if everything goes to plan, it will start to do its regression again. And at the end of these 22 seconds, we will also see a graph that displays us our data. Here we see, by the way, like how many iterations it is, how deep is it in. So it keeps us giving us feedback to where we are. And now we're here. If we take this and make it a bit larger so we can see this, you'll see in blue the truth, so where the values would be or should be, and in orange our prediction. So this is fine, I guess, but it's not too great. And as we've heard before from Eugen, we can do several things to this. But we're not going to do this in plenum because that would be boring, I guess. We've decided that this is now the step where you will try for yourself or with certain, with a little bit help of our friends.